For Notes 19, we're going to talk about something called least squares simple linear regression, or more commonly, just linear regression. So in the previous set of notes, we talked about correlation as a way of seeing sort of how related two quantitative variables are. And correlation let us understand sort of the direction and the strength of the relationship, but it didn't really let us make predictions. It didn't let us really understand like how those two things were related, just sort of how strong they were. And so linear regression is going to let us take that idea of correlation a little bit further. And so we'll start with an example here. Let's say that a consumer, they go out and they gather a random sample of 7 fast food burgers. So pretty small sample, but they want to see if they can predict how many calories are in a burger by looking at the amount of fat. All right, so when we previously talked about having two quantitative variables, we talked about two different kinds. We can have an explanatory variable, one that explains changes in the other variable, and we can have a response variable, one that responds to those changes. And so for this example, since we're trying to predict the number of calories, that would be our response. That's the thing that we're hoping responds to changes in the amount of fat. Fat is going to help us explain the calories in the burger. So to do this, we're going to start by using an applet that's on the course Moodle page. If you go down to the bottom, you'll see something that says Notes 19, Guess the Line Applet. And it'll load like this. And what I want you to do is to try to make the line look like what you would draw through this picture. So if you were trying to sort of describe the relationship between fat and calories, what might that look like? And so I might sort of start to move this line up, and looks like the intercept itself isn't going to do it for me. So let me try moving the slope also. And that's getting better. Maybe I think that that looks like a good line. So everybody who does this will probably stop the line in a slightly different place, right? Because we're just sort of eyeballing it, but we're trying to say, what would be a really good line to describe this relationship? So for me, I said an intercept of 176 and a slope of 11.7. But even when I did this a different time, I got a slightly different intercept and a slightly different slope. Because when we just eyeball things, we're not going to arrive at the same answer every time. And so one of the common things that we've seen in statistics is we want some way of saying what's best, like what should we do in this situation? What's the good line for this data? And to really understand that, the first thing that we need to talk about is something called a residual. So this is going to help us decide what the best line is. And a residual is just the vertical distance between what we actually saw and the line that we have. So for this example, here's my point, and this red line that I drew represents the residual. All right, so this is the distance between my line and the point. And remember I said vertical distance. So the way that we can calculate this is the residual is our actual response, or our y value, minus our predicted response. And so we call this y hat. Anytime you see this hat symbol over the top, you can think of that as like the predicted value. And so we saw actually something similar to this when we talked about proportions. P was the population proportion, and P hat was the sample proportion, which was basically our prediction for the proportion. All right. So for this example, it looks like maybe my actual response, my actual y value is, say, 490, and looks like the line is at about 540. So if I was going to calculate the residual, I would take my response, 490, minus my predicted value, 540, and I would get a residual of negative 50. And we want our line to be close to the points. We want it to really tell us like what is going on between these variables. So we want our residuals to be small, and you might have sort of tried to do this without knowing that it's what you were doing, but we probably want to balance out how many points are above the line, how many points are below, kind of how far above and below the line they are. And so your first instinct might be to say, all right, let's get a line so that the residuals add up to 0. Any negative residuals cancel out with positive residuals, maybe that's how we get the best line. And it's actually a really good first step. The problem is there's going to be a lot of lines that have that criterion. So there would actually be a bunch of lines where the residuals add up to 0. And so one trick that we use a lot of times in statistics, and you've actually seen something like this with the variance and the standard deviation before, is we'll take each of those residuals and we'll square them all. So now anything that was negative gets turned positive, and so we don't have to worry about the numbers canceling out and adding to 0. So we're going to square every single residual, and then we're going to add those up. And if our line is really close to our points, we should get a small sum of the squared residuals. And so a line that has a small value for that is going to be better than a line that has a large value. And you can think of this green box representing a squared residual. So I kind of covered it up, but there was a point right here. And so here's my residual. I just turn that into a square. And I want a line that would make all of these boxes as small as possible. And so there's only going to be one line that minimizes the sum of the squared residuals. So there's one line that has as small a value as possible when you add up all of those squared residuals. And I've got a note here that sometimes we also refer to that as the sum of the squared errors. So you might see both of these. So we can revisit the example that we just saw. And if you go back to that applet and there's a part that says secret code, we're going to type go stats here with this exclamation point. And another graph is going to pop up, and you'll see that here was my sum of the squared error, or sum of the squared residuals, 6,784.7, but there's actually another line that has a sum of a squared error of 6,746.7. So this one's a little bit better. And that line is actually going to have an intercept of 166, so let me try changing this, and a slope of 11.95. And you'll see that when I do that, now I've got a sum of squared error of 6,746.7. And I'm telling you that this is as small as you can possibly get. So let's say that I just barely increase my slope. So I go from 11.95 to 12. This number got a little bit bigger. So this is not quite as good of a line. Well, what if I had gone the other way? What if I went down to 11.9? Again, this is a little bit bigger, so it's not as good. I could try the same thing with the intercept. I move it down a little bit. My sum of my squared error gets a little bit bigger than it was before. I move it up a little bit. Sum of the squared error gets a little bit bigger. And you could keep trying this for, the next hour or so, and you're never going to beat this number. So there is one line that will give us the smallest possible sum of the squared residuals. All right? And coming up in the next video, what we'll do is we'll look at how to find that line and what it looks like. But for now, let's just talk about what a line looks like. All right? So you've probably seen the sort of general formula of a line from previous math classes. Y equals mx plus b. And m is the slope. All right, so for that line, it would have been the 11.95. And b is the y-intercept. Now in statistics, we use that same general formula, but we'll write it a little bit different. And we're going to have two different lines that we're going to talk about. So the first one, we're going to refer to as the true model. Basically, think of this as if you had data for the entire population. So for the fast food burgers, this would be if I had data on every single fast food burger in the world. I could talk about the beta 0, which in this case would be my true y-intercept for the entire population. I could talk about beta 1, which would be my true slope for the entire population. And basically what I would be saying is if I knew those two numbers, you could tell me x, you could tell me the number of grams of fat, and I would know the population mean response, so in that case the population mean number of calories, for that grams of fat. So there would be some sort of actual line that would describe the entire population. So I'm not going to know every single burger, but I would know on average, say burgers with 25 grams of fat have however many calories. But just like every other thing we've done in this class, we almost never have data for the entire population. So what do? We take a sample and we come up with our best guess. So rather than having y represent the population mean response, we're going to have y hat here, which will be our predicted value. So this is what we're going to predict. And we don't know the true y-intercept, so b0 is going to be our estimated y-intercept. b1 is going to be our estimated slope, and these two things are statistics. They're calculated based on our sample, and so they are our best guesses for those true values that we talked about. All right? So you can think of this like what we've done with previous examples. We wanted to know the population mean. Our best guess was the sample mean, and we could answer some questions using that. We wanted to know the population proportion. Our best guess was the sample proportion, and we could answer some questions from that. In this case, we want to know this true model, but we don't have data for the whole population, so we use our estimated model, and we can answer some questions from that. All right? Now, there are ways to calculate this by hand. We are not going to do that in this class. We're going to use SAS. And so in the next video here, what we'll do is we'll look at how we can use SAS to calculate this line, and then how we can answer questions using the line that SAS gives us.